Hello everyone, Professor Fiore here, and now we are going to have a little discussion on heat sinks, a very important part of any power application with semiconductors. So first, let's flip over to a typical Class B amplifier. Take a look at the power dissipation. Nothing special about this particular circuit. As a matter of fact, we're using small signal transistors over here, 3904, 3906 pair. Only 100 ohm load. This is the kind of thing that maybe you've set up on a breadboard in the lab. Now we're running on 10 volt power supplies, plus and minus. So in the ideal case, we might get 10 volts peak for the load, right? Whatever our power supplies are. In reality, you're going to get a little bit less. But in any case, if you had 10 volts peak, that would give you an RMS value of a little over 7 volts. You square that, right, 50 squared volts, divide by your 100 ohm load, and we're looking at about half a watt in the load. Now in the textbook, right, in the associated OER textbook that I wrote, and just a quick plug, it's free, go to the links and download it. There's a derivation that shows that for a simple resistive load like this, the dissipation on the power transistors, right, these two right here, is approximately 1/5 of the load. So in our case, if the load is half a watt, 500 milliwatts, that means each of these transistors is going to be dissipating, worst case, about 100 milliwatts, right? Not exactly high power, but we can investigate this through a simple transient analysis. So I've got a bunch of things here. Obviously, we've got the source, the load, I've got the voltage across the transistor and the current through it. So I'm going to separate out these curves so we can see everything. So for our interest right now, for the transistor's power dissipation, we want to just take the product of the current, IC, and the transistor's voltage, VCE. So you just multiply this curve by this curve, and what we get right now is this sort of looking thing, right? Obviously, where the transistor has turned off, in other words, when the PNP is conducting, we have nothing for the NPN. So no current, doesn't matter what the voltage is. If there's no current, there's no power. On the other hand, when it is conducting in the sort of push side of push-pull, then we have this sort of half sine wave pulse coming in here, and the inverse of that for the VCE on a DC offset, basically. And we get this interesting kind of curve, all right? Now, the true power of the transistor, of course, isn't this as far as the heating of the transistor goes, because there is a thermal time constant. Just like if you take a saute pan and you put it on the stove, it doesn't heat up the instant you put it on there and cool down the instant you take it off. There's a thermal time constant, just like, same thing like an RC time constant. It takes a while. So what ends up happening is this just averages out. We would find the area under the curve and average that over a full cycle and see what we come up with, right? So again, that proof is in the textbook. Now the question becomes, all right, if we have a half watt load, and that means 100 milliwatts for the transistor, is the 3904, 3906, are they going to blow up on the launch pad, so to speak? All right. Well, let's go and get a little bit of data, right, from the manufacturer. So the thing I want to focus in here on our 04 is this right down here in the corner, PD, total device power dissipation, 625 milliwatts, right? I mean, anything below, a watt or so is usually referred to as small signal, not really power with a capital P. But let's just see what happens here. We can still do a power analysis on a small signal circuit. So 625 milliwatts. That is, notice the second line, at 25 degrees centigrade, right? It's sort of a warm room temperature. We derate that at 5 milliwatts for every centigrade degree above. So here's a nice graph that appears later in the data sheet, and I just threw it over here on the side, blew it up so you could see it. So here's 25 degrees C, and in this particular transistor, this is using a TO92 case, which is this very common little plastic case, right? So it's saying, okay, this comes back here. This would be the 0.625 or 625 milliwatt level. And then as the temperature goes up, we see this thing drop off. Till finally we get out here to the maximum junction temperature, right, which is 150 degrees. And you'll notice that is over here, right? They say maximum storage and junction temperature range peaks out at 150 degrees centigrade. Okay, so that's this. So basically, for every degree you go up from 25, you're going to lose 5 milliwatts. So if we went from 25 to 75, right, that's a 50 centigrade degree change. Every one of those is going to be 5 milliwatts. Multiply that out, that's 250 milliwatts you're going to lose. All right, so here we are up here at 625. 250, right, would be 2 blocks, so that would be right here, and bingo, there you go, there's your 75 degrees, okay? So that's just the slope. What's the maximum junction temperature of a transistor? Well, it depends. 150, 175, maybe 200 for a big, juicy power transistor. All right, that's what we're looking at. Just to show you, right, here is a 3055, which is a very popular, been around for a long time, power transistor. This particular one, right, we're talking 115 watts. And there is, again, a D rate. I'll pull this down here a little bit. There is a D rate at 0.657 watts per centigrade degree. And you'll notice that the maximum temperature on this is 200 degrees, right? So here's our 25, right? There's the 115 watts. And for every degree you go above that, you're going to lose nearly 2/3 of a watt, okay? And this thing comes on down. Notice this is in a TO3 style case. There's only 2 leads here, right? There's an emitter lead and a base lead. The collector itself is the case, right? That's very important to remember. The case is the collector. Now, let's go back to this little 3904, all right? So it's a much more modest kind of device. The junction temperature doesn't go as high for a max. It's just a little plastic thing rather than a large metal case. All right, power dissipation is not nearly as high, but we can still do a power analysis using this. All right. As you can guess, though, this little plastic case cannot give up heat to its surroundings nearly as well as this nice metal case, which is several times larger. Right? This can produce heat, convection, radiation, and so forth, much more efficiently than that little plastic one can. But guess what? We can increase this even further by using a heatsink. So here's a little overview. The first thing I want to point out is heatsink is sometimes spelled as one word, sometimes it's spelled as 2 words, heat sink or heatsink. Your choice. It's just one of those kinds of things. The basic idea for a heatsink is you want to transfer heat from the junction away to somewhere else. Basically, in most cases, that would mean to the surrounding air, right? And it can do this more efficiently than the transistor can by itself. Normally, a heatsink is made out of aluminum. This would be the most typical thing. It's either stamped aluminum or maybe extruded aluminum, and the heatsink would be perhaps bolted on. It might be attached to the transistor with a little spring clip, maybe some other kinds of method of doing that, but they have to be in good, solid physical contact. And that creates another problem. Like I just said, the TO3 case, the collector is the case, right? In other words, the case is electrically live, right? The collector on your power transistor might be sitting at 75 volts. Okay, in our little example, it was only sitting at 10, but a big power amplifier, yeah, could easily be 75 volts or more. So do you want this big chunk of metal to be electrically live? Well, probably not. So you're going to need some kind of electrical insulator in there that will still allow heat to pass through. A typical thing would be a very thin little sheet of mica. Okay, there are also certain kinds of plastic films that are used for this, and we also use something called thermal paste to sort of fill the voids on these materials, so we get the maximum heat transfer through there. Okay, so that's sort of the basic idea. You can, in not so high power applications. Maybe use something like structural components in the chassis. I've literally seen power transistors connected directly to the chassis of an amplifier. And they use the metal in the chassis as the heatsink. Okay? You might, in very high power applications, use forced air. In other words, a fan. And very often, in a case like an audio amplifier, that fan will be thermally controlled. In other words, if the power dissipation is not very high and the transistor is not getting very hot, that fan will be at a low speed, or maybe it'll be off. And then as it gets hotter and hotter and hotter, we speed up the fan to get greater volume of air across there to remove that heat. The important characteristic, right, the numeric characteristic we're looking at is something called thermal resistance. And that's denoted theta, or sometimes as R sub theta. And the units on that would be centigrade degrees per watt. So you would find something that would say, well, the thermal resistance on this is 2 centigrade degrees per watt, which basically means if you feed it with a watt, there will be this 2 centigrade delta in temperature. Okay? Now, that's the case for a heatsink. You can look up a thermal resistance for a heatsink, and we'll do that in just a sec. But that's also true for the semiconductor devices. So there's a thermal resistance from the semiconductor junction to the ambient. And that would be denoted as theta JA or R sub theta JA, right? JA is junction to ambient. You might also find one that's junction to case, right? Theta JC or R theta JC. So let's flip back to the data sheet that we left off on, right? This is our 3904, and you'll notice right below the PD, here's an R theta JC, and they're saying, well, that's 83 centigrade degrees per watt, all right? And the junction to ambient, they're saying, well, that's 200 centigrade degrees per watt. Well, you think about that for a second. If there's a 200 centigrade degree rise per watt, and this thing only has 150 degrees centigrade maximum junction temperature, it's pretty obvious that you can't put 1 watt into one of these transistors, right? So, because that would literally be 200 plus the 25 ambient, it'd be 225 degrees centigrade if you put a watt into this poor transistor, right? Don't do that. If you were the transistor, it would hurt, okay? So that's what we see for this. Obviously, if we look at maybe our larger power transistor, right, junction to case on this is much smaller, right, 1.52 centigrade degrees per watt versus, as we saw before, 83. Now, if you think about this, theta JA, right, can sort of be thought of as in like 2 chunks. You can think of it as a junction to case plus, that's this guy, plus a case to ambient. So the difference between these two, you could think of as the case to ambient. The trick is a heatsink is more efficient than this case is. So this case is actually pretty lousy. When you think about that for a sec, 83 centigrade degrees per watt, but it's just this little plastic thing, right? How good is that? Whereas that TO3 case is all metal. Man, that thing can move a lot of heat, all right? So getting back to where we were, all right? Found these on a data sheet. Now let's go look at some heat sinks. So this first one, these are both using power tab transistors, sort of a TO220 derivative, or very common for what I would call sort of medium power transistors. You get a 50 watt power transistor, they'll probably come in a case like this. Anyway, this is a simple stamped aluminum, and this is an extruded aluminum. The picture doesn't really do it justice, but you've got these nice fins over here. There's a lot more mass involved, all right? And these graphs, let's just pick on this one first. It might be a little confusing because you've got like 4 labels out here, but basically these little arrows kind of give you a clue. For this curve, you use this and this, and for this curve, you use the guy on the bottom and the one over on the left, all right? So you can look at this in terms of heat dissipated. Right, how many watts dissipated? Oh yeah, there's 4 watts dissipated come up and across, and you can see there's going to be somewhere in the 25 degree range, right? This is mounting surface temperature rise above ambient. So, you would be looking at, 20 some odd degrees rise above ambient. The other way to look at this is to look at it in terms of a forced air situation where we have thermal resistance. So we have the thermal resistance coming up over here on the right-hand axis. Okay, this is again in centigrade degrees per watt. So you could come across here and you see, yeah, if I have a pretty good air velocity, 800 feet per minute, we're getting a pretty small value. It's a little over maybe 1.5 centigrade degrees per watt. And if we come down here to a much slower fan, maybe 200 or 300 feet per minute, now we're looking at somewhere in the vicinity of, 3 centigrade degrees per watt. If we compare that to this extruded, much more heavy duty sort of heat sink, we could see that those numbers are in fact superior, right? These numbers are lower down than these. Notice also there's an axis change over here, right? So if you think this one is flatter, well, this is only going up to 10 watts. This one's going up to 20 watts. So don't let that fool you, all right? So that's the basic idea. And you can find these kinds of data on your basic heatsink. You go to a heatsink manufacturer and they're going to show you this kind of stuff, all right? Okay, now how you do the computations. Here's the way to think about this. I've got a little diagram over here. Don't you love this drawing? So here's our junction, the little black square, and then the case. Then we have whatever the mounting interface is. So like I said, this could be like a mica insulator. Could be bare. It could just have like heatsink grease in here, something like that. And then here's our very fancily drawn heatsink. So think in terms of the temperatures. You've got a junction temperature, you've got a case temperature, you've got the heatsink temperature, and then you've got the ambient temperature. So I've drawn that out here, right? TJ, temperature of the junction, temperature of the case, temperature of the sink, temperature ambient. And we have a bunch, 3 to be specific, thermal resistance, right? Theta JC is what you get from junction to case. Then we have the interface, which is theta CS, okay, like the mica and so forth. And then we have the heatsink itself, which is theta CS, right? So that's, theta SA, sorry, sink to ambient. All right, so we already know we can look this up on a data sheet, theta JC for our transistors. We just did it a moment ago. Now, the interface is fairly consistent. I've got a nice curve over here, and this is for different kinds of interface materials. All the way on the bottom is just a bare joint. Right? There's nothing here. You're just going to bolt it directly on, meaning that, hey, this is going to be electrically live, okay? And then we have certain kinds of like plastic materials and mica and so forth. So, here's 2 different thicknesses of mica. So they're sitting over here. But in any case, these are fairly small numbers. You're getting a few tenths of a centigrade degree per watt. It's not a whole lot, okay? There's a little bit of variation with the torque. And as you can expect, if it's kind of loose, those are going to go up a little bit. But once you torque them down, and these are not heavy torque, right? This is measured in inch pounds. So not too strong of a torque there. But in any case, that does exist. Now, the last thing is, right, we pull the theta SA from the heatsink data sheet, right? That's what this is. So I've got the first one, right, the theta JC from the transistors data sheet. The second one, theta CS, which we basically pull from here, and then theta SA, which we pull from the heatsink manufacturer. Okay. Now, here's a nice little thermal model. You can solve this using a variation on Ohm's law. So we're going to make a little analogy here. And in our analogy, thermal resistance is represented by electrical resistance. So notice theta JA, and here's my resistor symbol. Temperature is equated with voltage. So if you see a voltage, that represents a temperature. So notice I have ground, that's absolute 0. I've got a little fixed power supply here, and its value is TA, the ambient temperature, right? That's what you are above absolute 0, all right? And then finally, the power dissipation is equated to current flow. So this looks a little weird, but I've got a current source over here, and it's labeled PD. So the power dissipation of the transistor, you think of that as a current flowing into this thermal resistance, and you can use Ohm's law, V is equal to I times R. So the temperature rise, which is the voltage, is I times R I is the power dissipation, PD, and R is the thermal resistance, in this case, theta JA. So you look at the units, your temperature rise is centigrade degrees, the power is in watts, the thermal resistance is centigrade degrees per watt. So when you multiply this out, obviously the watts and the per watt cancel, and you're just left with centigrade degrees. So this is what you have with that 3904 all by itself. You just have theta JA. Now, if you have a heat sink, like you would with that 3055, then you have the theta JC of the transistor, the interface, theta CS, and the theta SA of the heat sink. And here's the trick. As I said before, you could think of this as split into two parts, a theta JC and then a theta CA, case to ambient. Well, this stuff here, the heat sink, produces a lower number than that case by itself. Let's that sink in for a sec. Think of this as an electrical circuit. Hey, current's going to take the path of least resistance. So if this is a lower resistance, guess what? By our Ohm's law, thermal version of Ohm's law, that should be a smaller temperature rise. Right? That's the whole trick. You're basically sort of short-circuiting the case with the heat sink because it can dump heat more efficiently. So let's go to an example problem here, right? So I'm just saying we have a transistor and it's rated for a maximum junction temperature of 150 degrees centigrade. We look up on the data sheet, the thermal resistance junction to case is half a centigrade degree per watt. Now I'm going to use this transistor in an amplifier, and we require a 40 watt dissipation. In other words, the thing we did right at the front of this video when we looked at the transistor, we figured out what the power dissipation had to be. So we're going to say it's 40 watts. Now I have a heat sink. I look up on its data sheet. It has a theta SA, sink to ambient, of 1 centigrade degree per watt. If I use a typical interface, like maybe a mica interface, we're going to say, okay, maybe 0.2 of a centigrade degree per watt for that. And my question is this going to work? In other words, is this thing going to run below the maximum junction temperature of 150, or is it going to heat up and torch itself? Okay. So what we do first is we figure out what the thermal resistance total is. So junction to case, case to sink, sink to ambient. Right. By the way, some people, if you read the literature, the S, instead of saying sink, they'll say surface, meaning the surface of the heat sink. Either way, you know what I'm talking about, right? So add these up. So the theta JC was specified as half a centigrade degree per watt. The interface is another 0.2, and then the heat sink itself was 1. Okay, it's a pretty good heat sink. Add that all up, we got 1.7 centigrade degrees per watt. Now we use our thermal version of Ohm's law. The temperature rise is the power dissipation times total thermal resistance. So we need 40 watts. The total thermal resistance is 1.7 centigrade degrees per watt. Multiply that out, and there's a temperature rise of 68 centigrade degrees. So if we're operating at a nominal temperature of 25 degrees centigrade, just add those two numbers together, and we wind up with a 93 degree temperature, centigrade degree temperature for the junction. Well, 93 is well below the 150 that was the target, so this should work just fine. Done. If you come up with a number for TJ over here that's at or above the maximum junction temperature, no such luck. You are either going to have to find a better heat sink for that device or a device that has higher power dissipation. All right. You're probably not going to see, if it's the same case style, you're not going to see much difference on the theta JC for the most part, because it's really the formulation of that case, how the case is constructed, that makes all the difference. So you might get something with a different case style. For example, a linear regulator, voltage regulator for a DC power supply. These will come in different case styles. You can get them in TO220 cases. You can get them in TO3 cases. Obviously, the TO3 cases, even though functionally they're the same thing, the TO3 case has better thermal performance, so you can run it at a higher power dissipation, and it'll still stay below that maximum junction temperature, right? So that's what ends up happening. If you calculated, hey, it came out to 175, well, you got to come back here and say, well, okay, my 40 watt device isn't going to be good enough. Maybe I can get something with a higher junction temperature. Maybe I can get, go the other way, use the same transistor, but maybe get a better heatsink, right? There's, multiple ways of solving this problem. And really that's what engineering is all about, right? You have to balance all these things because I'll tell you right now, a more efficient heatsink is probably going to be bigger physically and more expensive. All right. Is it actually cheaper to buy a higher power transistor on that same heatsink than it is to, get a bigger heatsink? Maybe you don't have the physical space for the bigger heatsink. All right. It's a compact device. Hey, maybe I can crank up my fan. Remember, the heatsink can just be sitting there in stagnant air, but it's way more efficient if you have a fan blowing over it. So maybe I can get a slightly more powerful fan, get a higher rate of airflow, and we can go with that. All right. All right. Air velocity. All right. And what we see is we crank up that velocity and the thermal resistance goes down. Okay. All right. So that's our sort of hit on heat sinks. And the whole idea is basically a thermodynamic. In other words, I need to move heat from point A to point B. Point A being the semiconductor junction, point B being, the surrounding environment. Okay? All right, great. Hope you got something useful out of this. Oh, by the way, before we call it quits, you can buy heat sinks that are designed for multiple transistors. So don't think you just buy a heatsink for a transistor. So that original circuit that we were looking at, right, if this was scaled up in power, and these were, not an 04 and 06, but this was like a 3055, something big. You wouldn't necessarily have one heatsink for this and one heatsink for this. You could have one heatsink, and they're both bolted to that. And that's, again, another reason why they have to be electrically isolated. Because, this collector is sitting at some negative voltage and this collector is sitting at some positive voltage. And if they're both sitting on the same physical heatsink, you just shorted out both your power supplies. All right. But generally speaking, it's a lot easier as far as mounting and so forth if you take your power transistors and you just stick them on one big heatsink rather than trying to dole out individual heatsinks. It all depends on the application. So those are other things to consider. All right. Any questions? Put them down in the comments. We'll see you next time. Have a good one.